Okay, students, we're going to have a little discussion on the concept of center of mass. And when I was in high school, we called this the center of gravity. And sometimes you'll still hear that phrase being used. You'll hear me use it. And center of gravity is not necessarily a poor term. It all depends on how you define the system. So if we take, let's say this is you and this is the center of Earth, right? And we want to find the balance point between those two different masses, like the fulcrum of a seesaw, right? Then we would call that the center of mass. And in this system, though, since it's determined with the force of gravity, it happens to be the same. So the center of mass and the center of gravity would be the same in this system. Okay, you would use slightly different math, but you'd find out that it would give you about the same answer. Okay, so you remember Newton's universal law of gravitation, all right? So you would use that, right, to find what the force of gravity is between these two objects. Right, it'd be the same, right? But where's the location where you would have the center of gravity between these two objects? So it's not necessarily half of this, which is what most people might think. If you want to know where, half of the force of the gravity is on one side and half of the force of the gravity is on the other side, it's kind of hard to think about that in this system like this, right? Because you can't think of yourself ever being on a seesaw with the Earth. You are familiar with working with this equation, right? So anyways, you could see that your effect, your mass's effect, and wherever the center is of this system is going to have very little effect whatsoever. And you would find out that the center of gravity and the center of mass would be almost right here. Well, it'd be pretty much the center of the mass of the Earth, right? Now, if you're in outer space and there's no celestial body near you, right, then you can talk about the center of gravity, all the masses, right, the endpoints of all these masses, attracting, like this, the mass right here is going to be attracted by that mass there. That mass is going to be attracted, this mass. So you're going to have all these force of gravity attractions. We learned way back in the beginning of school that this force of gravity attraction at close distances is pretty minimal. But what you would probably find in this situation is that the force of gravity, right, between all these objects and the center of mass, may not be the same for everyone. It might not be the same, but it also would be close. The center of mass and the center of gravity of this whole system would probably be close to the same place, right? It's just how that turns out. So the use of the phrases center of mass and center of gravity could be synonymous depending on how you define the system and exactly what question you're asking. But for simplicity's sake, we'll use the phrase center of mass because that's what we'll be using. That concept is what we will be using when we study rotation. Whenever you're looking at something rotating, you always want to consider it rotating around its center of mass. So center of mass is very important in rotational motion. And so we'll try to stick to the phrase center of mass, but just be aware if you look at any videos, even if you read some texts, they will interchange, they will use center of mass and center of gravity interchangeably. So you have to make sure that you are understanding what they're referring to, okay? All right, so why, other than rotation, why is center of mass important? You use it all the time. I had to find the center of mass of my iPhone, and in order to mount it on this round little pole here, right? iPhone is rectangular. I had to mount it on a round pole in order to make this video, and I had to find the center of mass. Now, I did this intuitively. I didn't get out a calculator and calculate it. I did it until I could get that iPhone to balance on this round pole. You use center of mass a lot, right? We see it especially in sports. We see it in any kind of sport that requires a lot of balance. Sports that come to mind right now, figure skating, gymnastics. You'll see center of mass being exhibited. It's pretty prevalent in those sports. Ballet is another place where center of mass is really important. And a lot of dancers will tell you, man, it's all about finding your center, right? What they mean is their center of mass. If they have a good idea how to locate that center, then even if they get off balance for a split second, they can find that and recover. And probably someone in the audience didn't even know that they were starting to lose their balance, depending on what they're doing. You know, when you think about them dancing on their toes, right? It's very little area, surface area there in contact with the floor. So balance is really important. So, you know, you're going to see center of mass used in a lot of places. You go get your tires rotated on your car, they balance the tires, right? So that your car runs smoothly. So center mass is very important. One of the things I did want to talk about is that you don't necessarily have the center of mass inside the object of concern. Like, let's say this is a solid object. Its center of mass might actually be outside of the object, right? And it's this concept that, back to the sports analogy, where the Fosbury flop was invented, right? You have people going over, this is the high jump event in track and field, people going over that high bar, right? And they do it, if you ever see it, they jump over with their shoulders and head first, right? And bend their body. And their center of mass is actually under the bar, right? So that now they're taking advantage of the concept of center of mass in order to clear the bar there. So I'll post a video so you can look at that. I'll try to find some ballet videos too. My oldest daughter was in dance for, 12 years or so. So I was around the whole dancing community for a long, long time. Okay, so let's take a look at a couple of problems. Okay, so hopefully I'm putting this back where it was. I can't see what the camera's pointing at, so hopefully you guys can see this. So let's take the Moon-Earth system, right? We're defining this as the system here. And we want to figure out where is the center of mass of this system. Okay, so what are some of the variables you need? You need to know the distance from the center of mass of the moon to the center mass of the Earth. And you need to know what the mass of the moon is. You need to know what the mass of the Earth is, right? And that's pretty much it for now. Okay, so the question that we're trying to tackle here is, where's the center of mass in the Earth-Moon system? So there's a standard equation that we'll use. Now I modified it because we just have two objects here. You can find center of mass, you can have infinite number of objects and find the center of mass, right? So you could continue to add objects, right, as the problem dictates to you. So here I'm going to say that Earth is M1, right, and mass of the moon would be M2. The distance from the moon to the Earth, so the Earth center mass of the moon to the center mass of the Earth is x2, right? And we have to have a starting point somewhere. So we'll say that that starts at the center mass of the Earth. So we'll make that x1, and that's going to be our starting point, 0 meters, right? So if we do the mass of the Earth times 0, that's 0, so this drops out. So then you just have the mass of the moon times this distance divided by the mass of the Earth plus the mass of the moon. Okay, and that gives you the point of center of mass of this system as measured from your point 0. Okay, so this is the answer that you should get. I gave you the sig fig answer too, just to get in practice of finding sig figs again. So make sure that you are practiced up on that, especially before the AP test, right? So this is what's really interesting, right? The interesting part of this is not the math and finding the answer. The interesting part is the fact that the center of mass of this system is actually inside of the Earth, right? It's below the surface of the Earth somewhere. It's probably, proportionately, it's probably about right here, right? And for this reason, I think it's important for you to know that this is what these two objects rotate around. So the Earth is actually rotating around the moon, and the moon is rotating around the Earth. We only see the moon rotating around the Earth. But in actuality, both of these are rotating around the center of mass, okay, which is, I think, is kind of cool. This also contributes to the wobble that you hear astronomers sometimes talk about, the Earth's wobble. Earth's wobble, and it not only does it wobble on its axis as it rotates, but it wobbles in its revolution around the sun. That wobble is caused by that pull gravity from the moon. Okay, so pretty interesting. Okay, let's take a look at another problem. All right. So here we're going to do a seesaw problem. Hopefully I have this set up for you guys. You can't see my camera. Hopefully you can see it. Okay, so we have a dad and a child seesawing. All right. And we want to, when you go to some of these playgrounds, you can actually change where the fulcrum is on the seesaw. So I tried to make this as realistic as I possibly could. With a couple exceptions. I just, you'll see. But for the most part, I tried to make this pretty realistic. I remember when my children were little, always trying, doing the seesaw with them, and they thought it was pretty cool that it was equal effort for their dad and for them on the seesaw. So they kind of like that. Okay, so here's our setup. We have a dad, we have a child, we have a seesaw, 5 meters. That's pretty long for a seesaw. This is probably the only thing that's not realistic, but I think it's probably close to some of those bigger seesaws you see at some of the playgrounds. And we want to know where to put this. We want to put this fulcrum right at the center of mass. So how do we do that? First of all, we want to set up our table of data, right? So get back in the habit of doing that, showing how you've set up the problem, right? And a couple of things that I noticed that, just like you guys, I'm kind of rusty too, right? After trying to figure out what to do over the last couple of months. I put all the units here. I could have just put the units up here in the heading of the column, right? And then just put down the values. So that's what I did over here. I put meters up here, and then I put the values here. All right, so for the seesaw, right, how can you put the distance of the seesaw, you know, to this from the center of mass of the seesaw to the starting point, when part of the seesaw is at the starting point? That almost seems counterintuitive. But what you use is you just use the center point of the seesaw. So it's 5 meters, or the center of mass of the seesaw itself with no people on it will be at 2.5 meters, right? Okay, so these are the values that we're going to use. Go back to the center mass equation. I don't think this equation is on your cheat sheet, which is another reason why I wanted to go over this. Okay, so we set this up. We said dad was at 0.0, right? And then I have, you can call any of these others however you want. You know, you could call this M2. You could call this M3 if you want. We can do it like this. We'll put M1 here, M2, M3, if you want to do it that way, right? Dad's mass times 0 is 0, so that falls out, right? So you're just going to use the mass times the distance to the starting point, right? Plus mass 3 times, and then this would be from its center of mass to the starting point, okay? So x2 would be from here to here, and x3 would be from the middle to here. And here are your masses, and we're trying to find the center mass, or the distance from the starting point to the center mass, x center mass, right? And when you do this, you should find that answer with sig figs. That's your sig fig answer. Okay, I hope this helps. I will put some practice problems on Blackboard for you, and we'll get into more details of rotation next lecture. Thank you. Bye-bye.